This is the second lecture for chapter 15. We'll have a third one posted before too long. But in chapter 15, we are looking at substitution reactions at sp3 carbons. To be more specific, it's nucleophilic substitution reactions at sp3 carbons. So in this lecture, we will look at the following. We'll look at another mechanism that we'll call the unimolecular substitution, or the SN1 reaction mechanism. We'll next concentrate on some features of this type reaction, such as the electrophile. Then we'll also look at features such as the nucleophile and the solvent that we'll use. We'll also look at the stereochemistry of the products. So what we will be doing is to compare these with the SN2 mechanism. Then we will look at a detailed mechanism for the SN1. This mechanism for the SN1 is a bit more involved compared to the SN2, which we covered in the previous lecture. And lastly, we'll do a summary for the factors that influence the SN1 reactions. Okay, so let us begin. So let's look at this reaction that we know to be a substitution reaction, where we have the electrophile, which has a leaving group, and we have a nucleophile, which has a pair of electrons. And in the substitution reaction, the leaving group leaves with its electrons over here, as shown over here, and the nucleophile bonds to the electrophilic carbon to make a new bond. So last lecture we looked at a mechanism that explained that, or one mechanism, and that was the SN2 mechanism, where the nucleophile comes in from the rear and kicks that out. But in this lecture we will consider another mechanism to explain the same reaction. So it's the same substitution reaction, but another way of explaining it. So let us see what this mechanism is. It is a two-step mechanism, or there are two steps in this mechanism. So let's look at the first step. So in the first step, we have the electrophile, which has a very good leaving group. The key word here is a very good leaving group. All by itself, it decides to leave with its bonding electrons. Notice the movement of electrons. It's a double barbed arrow to indicate two electrons from this bond here going to the leaving group, and here are those two electrons. What's left behind on this carbon here is a positive, and of course, as you know, that's called a carbocation. This step is a slow step, hence we call it the rate determining step, or the RDS. So once again, the electrophile all by itself, one molecule, the leaving group leaves with its electrons to form a leaving group as the product, and a carbocation intermediate. Notice this is an intermediate, it is not the product. In a second step, as shown here, the nucleophile, which has a pair of electrons and is negative, of course, because they are electrons, bond to the positive carbocation. Once again, remember that electrons are negative and carbocations are positive, so they will attract because opposites will attract. This reaction, as you can imagine, is very fast. because we have electrons that are bonded to a positive. So that's a fast step in the mechanism, which is the second step of the mechanism. And here we have the substitution product. So this is the overall mechanism, or the overall two steps for the mechanism. The electrophile, in the first step, the leaving group leaves to form a carbocation, and the leaving group in a rate determining step, or the slow step. In a second step, the electrons of the nucleophile bonds to the carbocation as indicated with this arrow here. Notice my arrow, double barb, to indicate two electrons bonding to the carbocation, which is positive in a fast step. Now, why is it called unimolecular? It's called unimolecular because in the most important step of this reaction, known as the rate determining step or the slow step, only one molecule is involved. So it's a unimolecular, one molecule, the electrophile, and of course nucleophilic substitution. So it's called an SN1 mechanism for this reaction. We can represent this mechanism using the energy profile diagram. So we start off here with the reactant. Notice this should be reactant, which is just one molecule. It forms the carbocation. Notice the energy of activation here is pretty high because it is the slow step, the first step, or the rate determining step. And in a fast step, the nucleophile bonds to the electrophile. Notice again this energy gap here, or the energy of activation is much smaller because that is a fast reaction to give here the products. So this is another way of representing the SN1 mechanism. Two steps. First step is the rate determining step. One molecule involved, the electrophile, and in the second step, it's the fast step. Let us look at a reaction, an SN1 reaction. So here's our electrophile, here's our nucleophile, and it's a nucleophile because, of course, as we know, it has two pairs of electrons. So that makes this oxygen here the nucleophilic atom. This atom here is the electrophilic atom of the electrophile, and bromine is the leaving group. And it's a good leaving group because, of course, as you know, the bromide anion is a very weak conjugate base. So in a substitution reaction, the bromide or the bromine takes the electrons to form the bromide. The nucleophilic oxygen bonds to the carbon, and here is the new bond that's formed. And of course, oxygen takes two bonds, so one of these hydrogen bonds to the bromide to form the HBr product. Let's see if we can use the mechanism we just described to explain this reaction. So in the first step, the bromide leaves as indicated with this arrow here. Notice whenever we ask you to write a mechanism, we always say using arrows to indicate electron movement. This is exactly what we mean. So this bond breaks, and of course here are the two electrons that comes from the bonding, and what's left behind is a carbocation. Water is a solvent. It's a good ionizing solvent because it is a polar protic solvent. So it will assist in breaking that bond. to give the bromide anion and the carbocation because it's an ionizing solvent and it aids in ionization. This process is also called ionization. In the second step, or the fast step, as you can imagine, water, which has a pair of electrons here, quickly bonds to the carbocation, and this, to be more specific, the carbon of the carbocation to form this bond right here. As you know, oxygen takes 2 bonds. If it has 3, it's an intermediate and not stable. So 2 electrons here can come in onto the oxygen to form the alcohol, and of course minus H plus. So this H comes off as H plus. So this is the mechanism for the substitution reaction given here. It's SN1 because in the initial step we form a carbocation. Notice in the SN2 we do not form an intermediate. It's a concerted reaction, one step. This reaction is also described as solvolysis. Why? Because the solvent, here's a solvent, is also the nucleophile. So SN1 reactions are also described as solvolysis because the solvent, which is the ionizing solvent, is also the nucleophile. Let's look at another example. Well, let's conclude. So going back here for a second, we notice that a carbocation intermediate is formed. So as you can tell, once you have a carbocation intermediate, there are different stabilities depending on the groups bonded to this carbon. This is a secondary carbocation, but it's possible to have a reaction go and it generates a tertiary carbocation. And since this is the rate determining step, the overall rate of the reaction depends on the stability of this carbocation. Let me just emphasize that again. For SN1 reactions, the most important step of the reaction is the first step, or the rate determining step, which generates a carbocation. The overall rate of the reactions that go by SN1 reaction mechanism depends on the stability of the carbocation generated here. So on the next slide we have a summary. If the carbocation generated is a tertiary, it is very favorable because tertiary carbocations are very stable. If the carbocation generated is secondary, it's reactive, but not as reactive as a tertiary carbocation that's generated. And of course primary reacts, but the methyl definitely does not react by SN1 because the primary carbocation is not stable. So the summary, these two, the tertiary and the secondary, are the type carbocations that's generated in the first step that we need to be concerned with. Another way of stating this is the electrophile should be tertiary. So if we have a carbon bonded to a leaving group, depending on the 3 groups here, if there are 3 alkyl groups, which makes it a tertiary electrophile, this is more reactive than a carbon that has a leaving group that has 1 H and 2 R's bonded to it. And of course, as you can imagine, it's more reactive than a carbon that has a leaving group and has an R and 2 H's, making it a primary electrophile. So these two type electrophiles are the most reactive by SN1, and the tertiary electrophile is the most reactive. I should remind you that this trend is the exact opposite of that for the SN2, because the mechanisms here are different. So it's the exact opposite. Let us apply what we've just discussed. So comparing these pairs of electrophiles, which is more reactive? Here's the electrophile because it has a leaving group, and here's the electrophilic carbon. So this type electrophile is a secondary. This type electrophile is a primary because this carbon that has the leaving group is bonded to just one alkyl group. Of course, we have here two hydrogens. So this is a primary chloride. So this is more reactive by SN1. This type electrophile is a tertiary because here's a carbon that has 1, 2, and 3 carbons bonded to it. So it's a tertiary. Here is a secondary electrophile or secondary chloride. So this is more reactive. This is a secondary chloride. It is more reactive than a methyl. As a matter of fact, the methyl will not react by SN1, so this is the most reactive. Here's another methyl chloride. This time it's a tertiary chloride, so this is a lot more reactive than this one, which is not reactive by SN1. Okay, let us apply this to another reaction. So here's a tertiary bromide. Here's our nucleophile. Why nucleophile? Because the alcohol has an unshared pair of electrons, at least one, it has two. So this is our nucleophile. Here's our electrophilic carbon. Here's our leaving group. So the organic product is as shown here. It's SN1. Why is it SN1? Because the solvent is an ionizing solvent and it's protic. Remember, it is CH3 that's bonded to an H and an oxygen and bonded to an hydrogen. Since this oxygen is electronegative, it's partially negative, and this hydrogen is partially positive, so therefore this is a protic because that hydrogen acts like a proton, and don't forget a proton is H plus by definition. So methanol is a protic solvent, so it's an ionizing protic solvent, so this reaction mechanism occurs by SN1. Tertiary. Of course, we would not expect it to go by SN2 because it is tertiary. And another reason why it would not go by SN2 is because the solvent is a protic solvent. Here's another reaction. This one, it's a secondary bromide. Here's a solvent. Again, the same solvent, which is a protic solvent. A protic ionizing solvent, so we would expect SN1. This is secondary, so that could go by SN1 or SN2, but this is a giveaway that it will not go by SN2 but will go by SN1 due to the solvent. The product, as you can expect, is here where the bromide leaves, the bromine leaves as a bromide, and the H here is bonded to form HBr. Let us look at the stereochemistry of the products. Remember, for the SN2 we had an inversion because the nucleophile had to come in from the rear and invert the stereochemistry to produce the product. For the SN1 mechanism, however, a carbocation is generated. So if we start out here with an optically active electrophile, once the bromine leaves as a bromide, as shown here in the rate determining step, a carbocation is generated. You may recall that a carbocation is trigonoplanar, which means that it's flat. It has here a vacant p orbital, unhybridized p orbital, which means that the nucleophile can come in from the top or the bottom. There's an equal probability of coming from either side because it's completely flat. And of course there is an equal mixture of the alcohols or the products. If you have an equal mixture of a optically active molecule, that's called a racemic mixture. So the SN1 reaction, if the reactant is optically active and if the reaction proceeds by an SN1 mechanism, the products are optically active, but, keyword here is but, there is an equal mixture of both to get a racemic or an S product. Now that's completely different from the SN2 where you only get one optically active product, and that's the inverted product. So as we look forward, if you're synthesizing an optically active molecule, you do not want to use an SN1 mechanism. You want to use an SN2 mechanism. We'll do that in the next lecture anyhow. So let us look here at a couple more examples. So here's a secondary bromide reacting with an alcohol, going by SN1. Why SN1? Because this is a protic nucleophile which can act as the solvent. So it's a protic solvent or an ionizing solvent. So we get a mixture of optically active product where there's retention of configuration because they're on the same side, or inversion of configuration because they're on opposite side. Written differently, this, of course, as you will recall, is the Fischer projection. So written a little differently in the Fischer form is this molecule, and reacting with this as the solvent and the nucleophile, we get a racemic mixture of R and S products. Don't forget that mixture. Okay, let us concentrate now on unexpected products. You'll find this a lot for SN1 mechanism. So let's look at this reaction here. So this is the electrophile. This is our nucleophile, again, because we have these two electrons here. So for the expected products, you would expect that this bromine to leave, and this would bond to that carbon to make this bond. Of course, we have here HBr. So this is expected. However, if you went in the lab and carried out this experiment, you would also get this product as the unexpected product. Let's see if we can make an observation to see the difference. Notice this carbon here has two methyl groups. Over here it just has one. This carbon here has one methyl group, but over here in the product it has two. So I think you know what's happening here. There is a migration. So let's see the mechanisms, or the mechanism. To explain the expected expected product. This bromide leaves with its bonding electrons to form the carbocation right here, and the nucleophile comes in as shown here to form this intermediate. The bromide takes that off to get HBr, and this is our expected product, where that's the bond that's formed. Nothing surprising there. But let us look at the unexpected product. In this case, the bromide comes off in the RDS as expected, but it forms here as shown a secondary carbocation. I shouldn't say but, it does form a secondary carbocation, which is the same as shown on the previous slide. Here's the key. This secondary carbocation can rearrange to give a more stable tertiary carbocation. This change occurs because this methyl group with its electron migrates as shown with this arrow here. So this is called a 1,2 methide migration. Why 1,2? Because it moves from one carbon to another carbon adjacent. So it's 1,2. You'll see in some books an alpha beta using the Greek alphabet or terminology. It's called a methide because it's a methyl group with its bonding electrons that moves over to here, and what's left behind is a carbon, which is a carbocation, but now a tertiary carbocation and more stable. In the other step, we'd expect the nucleophile to bond to the carbocation as shown with this arrow here to form this bond, and of course the bromide takes this off as a proton to get HBr, and these electrons here swing in as shown here by this arrow. So this is the unexpected product that's produced by the rearrangement of the secondary carbocation to form the more stable tertiary carbocation, which in a fast step goes to form the product. Let us look at another type unexpected product. So here is our electrophile. As you can imagine, this carbon here is now an allylic carbon because it's bonded to or adjacent to a carbon-carbon double bond. This is our nucleophile, as you can imagine, and also our solvent. It's a solvolysis going by SN1 reaction. This is expected because, as you can imagine, if this leaves with its bonding electron to get Cl minus, this OCH3 can bond right here to get this product. This is unexpected though, because notice the OCH3 is not bonded to this carbon. So doing the analysis here, or the observation, this OCH3 seems to be bonded to this carbon. The question is, how does that happen? Let's see. So in the first step, as you can imagine, this bond breaks, leaving group leaves and taking its bonding electron as indicated with that arrow to give Cl minus in the rate determining step. This is our carbocation. But it's a special carbocation because it's an allylic carbocation because it's adjacent to a carbon-carbon double bond. We can draw resonance structures as shown here with the arrow to put the positive charge over here from here. So that's a delocalization of the positive charge. Remember again that resonance is just a delocalization of charge across atoms. And we use arrows to indicate the movement of electrons so that we can see the charge movement as shown here. So as you can imagine, the OCH3 nucleophile, if it bonds to this carbon right here, we have our intermediate, and of course since there are three bonds here to oxygen and it needs two, these electrons come in to form the product and we have H plus coming off. So this is the expected product. Let's see how we form the unexpected product. Same initial step, RDS, forming our carbocation. This time again, or should we say again, it's the allylic carbocation. We can draw resonance structures, put in the positive charge on this carbon. So now we have our nucleophile coming in and bonding to this carbon here, making this bond right here. And of course, since we have three bonds to oxygen, the chlorine will take off, or the chloride, should I say, will take off this hydrogen as a proton to get HCl, and this becomes our product. So this is our unexpected product. And it comes about because the initial intermediate that's generated is resonance stabilized, moving the charge from this carbon to this carbon, and we can have attack from the nucleophile on the carbon to give the unexpected product. So let us look here at another reaction or reactant or electrophile. Looking at this molecule, which is an alcohol, you can see here it's an alcohol because it has an OH bonded to this carbon. The question now is, can we have a substitution reaction at an alcohol, a carbon that has an OH group? The answer is really very, very hard, because this OH here is a very poor leaving group. You may recall that if it left, it would be OH and electrons, 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 and most importantly, minus. That's the hydroxide ion or anion. Of course, as you know, that's a strong base, because sodium hydroxide is a strong base. So this OH group is a very poor leaving group because it is a very strong conjugate base. Remember, to have a good leaving group, we need a very weak conjugate base. So this is a poor leaving group, so this reaction is very difficult to occur. In the presence of an acid, however, HCl, the reaction occurs. So if you went in the lab and you mixed an alcohol with HCl, you do get a substitution reaction where this Cl here substitutes for the OH, and of course we have HCl. The question now is, how does that occur? That occurs because here's an acid, partially positive. Of course, as you know, HCl is a very strong acid, and here is a pair of electrons. So these electrons can bond to this proton here of HCl to form this as our leaving group now. So it's now a protonated OH. The conjugate base here is H2O. As you know, this is a very weak conjugate base. Water has to be, because we drink it every day. So it is a very weak conjugate base, making this a very good leaving group. So on the next slide, we have it showing as a leaving group. So here it is, leaving with its electrons to give water. Very good leaving group. Leaving behind a carbocation, positive charge here from this electrophilic carbon in the rate determining step. In the fast step, the chloride anion, which is generated from HCl, is our nucleophile, and this arrow shows the electron movement to this carbon here to form this bond right here, which is our substitution product. So once again, these reactions with alcohol will occur, but we need to protonate it to get here a better leaving group. So here is a reaction. Here's a tertiary alcohol. Here is the OH group, very poor leaving group. But in the presence of HCl, a strong acid, we'll protonate this OH to get OH2, a good leaving group. Here is our nucleophile, and here is the new bond that's made, and here is our leaving group, and here's the product. This is the substitution product. Notice that this is a tertiary alcohol. This reaction here is a reactant that's using a secondary alcohol. Same reaction conditions. But in this case, we would form a tertiary carbocation, and here we would form a secondary carbocation in the RDS. So we would expect that this reaction here is more favorable than this reaction here, which involves a secondary alcohol, which again reinforces that a tertiary electrophile, even though it's a very poor leaving group, but in the presence of an acid, is more reactive than a secondary alcohol in the presence of an acid. As you can imagine, a primary alcohol is even a very much slower reaction because it forms a primary carbocation. As you'll see in the book, this is used to test for the type alcohols that are present. It's called the Lucas test. So if you mix a tertiary alcohol with a HCl, it's a very fast reaction. And if you mix a secondary alcohol, it's not as fast. Okay, conclusion. So, for the SN1 reaction, or the substitution reactions that go by SN1 mechanism, here are some important observations. The mechanism, it is a two-step mechanism in which a carbocation is generated. Key. That's different from the SN2, where a carbocation is not generated. The electrophile. The electrophile here, the allylic or the benzylic, is more reactive than the tertiary and more reactive than the secondary. And of course we say that these two here more than likely will not react by SN1 because of the stability of the carbocation that's generated in the RDS. These are not stable carbocations. Stereochemistry. Because of the carbocation that's generated in the RDS, which as we said is sp2 and flat, we have here a racemic mixture of products. We say it's optically inactive because it's an equal mixture of enantiomers. The nucleophile. The nucleophile is typically the solvent, or for our case it's just about always the solvent. And that's why these reactions are also referred to as solvolysis. Solvolysis because the solvent is the nucleophile. So you can imagine that size does not matter because that's in the fast step. Because the step that determines the overall rate of the reaction is the RDS. And the nucleophile is not used in the RDS but in the fast step. Leaving group. Need an exceptionally good leaving group. Exceptionally good leaving group. Why? Because in the first step, the Electrophile generates the carbocation. Remember that good leaving groups are weak, stable conjugate bases. The solvent, as we mentioned earlier, has to be ionizing protic solvent. And the solvents are typically or always the nucleophile, and these type reactions are called solvolysis. So that's SN1 reaction. So I'll get out a set of tutorial questions so you can practice these reactions. As you can imagine here, the type questions that you'll get is to ensure that you understand the mechanism, because it's a two-step mechanism in which a carbocation is generated, and a lot of different aspects can happen to a carbocation, such as rearrangement and of course resonance, giving unexpected products. So look out for that. So continue to study, get your book and read along as you watch the video. I'll post these PowerPoints online, and I'll get your tutorial questions out, which will be due on Wednesday. So continue to study hard and get ready for the quiz that's coming up, and you should be okay.